Pues si quieres.
Ay, gracias.
A ver, pues tienes un virus, no, como me lo sé.
No, si lo quería también.
No, bueno, pero
Ahora tú toses y escupes a la gente.
escupes literalmente. Mira, si escupes en la cara de la gente, vale, pero si escupes en la...
Ya, eso está feo.
Bueno. Estabas aquí. Esta de el ángulo muerto de las gafas. O sea, si no tengo que verte bien, oye, no veo nada, tío. ¿Cómo le hacéis de gafas? ¿Cómo lo hacéis? Pillando.
Pues no, no estamos mal.
Con esto, pues movilla.
No se está grabando.
No, al revés, ahí. Poniendo los comandos encima de él. Okay. I think we can start. It's a pleasure to introduce you to Xavier López López. He studied the graduate in Valencia and then moved to Tenerife for the master. And he worked with me in the TFM. After that, he moved to Bologna to do the PhD in synthetic catalog for future surveys. And this is what he's going to talk about today. Thank you very much.
Yes.
And all yours.
Okay, thank you, Juan. Thank you very much for being here, and thank you for the invitation. So yeah, my name is Xavier López López, and today I'm going to present you about this work. But first, okay. First technical problems. Okay, we'll use the like this. Sorry. Okay. So first, well, Juan Antonio already introduced me, but I wanted to introduce myself a bit. As Juan Antonio said, I studied in Valencia. Then I moved to La Laguna to study astrophysics, where I did my master thesis co-supervised by Juan Antonio on low luminosity AGN. Then I moved to Bologna to do my PhD, and the work I'm going to present today is the work that I have developed during my PhD. And right now, I started a postdoc with the same supervisors, and we are continuing the work of the PhD, and also we are starting to look at the first data from Euclid, and especially from the spectroscopic side. So, more technical problems. Okay. So I prepared a bit of a wide introduction because I was not sure about the context of everyone. So first, I want everyone to understand the title of the talk. And we are going to start with the first word, AGN. So probably most of you know, but very quickly, AGN stands for active galactic nuclei or nucleus. They are defined observationally as usually powerful sources, even though they can be also with much less luminosity, emitting in multi-wavelength emission, although again, this cannot be true. It can be that some of them do not emit in radio, nautical, etc. And what is true for all of them is that this emission comes from the central region of the galaxy, and in some cases, the emission from the AGN can outshine.
It's there. Let's try this. This is an electrical contact.
Ah, okay. Okay. And in some cases, the emission from the nucleus can outshine the host galaxy. As we see here, the emission from the AGN in mid-infrared to hard X-ray. The color one is the one from the AGN. Okay. While the gray line is the one from the host galaxy. So how do we model this powerful multi-wavelength emission? Well, in the 90s, people developed the unification model. The main components of this model is that in the center of the galaxy, there is a supermassive black hole, and matter is accreting into the black hole. This explains the optical and UV continuous emission. There is a dusty torus around the supermassive black hole, which explains the infrared emission, and also, depending on the orientation with which we look at the AGN, explains the different types of AGN that we can observe. there is also the broad line region and the narrow line region, which are gas clouds around the supermassive black hole, which explain the narrow lines. And also, very briefly, the corona and the jets, which explain the X-ray and the radio emission. So now that we saw the physical model, we can come back to the observation, and we see that actually the AGN can present a very rich phenomenology, in which, depending on the angle that we look at it, which explains the different obscuration and the power of the central source in this axis, we can have different phenomenology, including some in which the host galaxy can almost totally dominate over the AGN. I want you to get from this slide also that even in the cases in which the AGN is less powerful and obscured by its torus or other material around, usually we can detect AGN with hard X-ray emission. Now, very briefly about the optical spectroscopy of AGN. Usually AGN are separated into type 1 or type 2. Type 2 are unobscured, therefore we observe them without obscuration from the torus. And in type, sorry, I said type 1. I think maybe every time I press. No. Or maybe
I think it's some electrical contact, but I don't think the problem is there because I changed the switch. It might be the cable, but the cable cannot be changed because it's
okay. Okay, I think we can survive like this. So in type 1, we can observe both narrow and broad lines. When I say broad, I mean this type of Doppler broadenings. While in type 2, we can only observe narrow lines. I want you to get from this slide that these can be used to separate type 1 from type 2 AGN, depending on the full width half maximum. And also we can use the narrow lines of type 2 AGN to separate them from star-forming galaxies. So now let's have a quick look into what I mean with future or even current surveys. With this, I mean surveys that will cover unprecedentedly large areas of the sky, and they will gather photometric and spectroscopic data for billions of galaxies and millions of AGN, we expect. So we really need to be ready for these vast amounts of data. Some examples of this type of surveys, for example, from space, we have Euclid or the Roman Space Telescope looking in the optical and infrared, and Rosita looking in the X-ray. From the ground, we have the Beira-Sea Rubin Observatory, currently in construction, or the JPAS survey, which you all know very well. For the rest of the talk, I will focus mainly on Euclid when I will show you some applications of the catalog. So I wanted to show you some more technical details. Euclid was launched in 2023. It will cover a wide survey, which is what you see here in blue, with 15,000 square degrees, and also a deep survey of 53 square degrees, which is the ones you see here in yellow. And it's equipped with two instruments, one to look in the visual range and one to look in the near infrared range. Here you can see the photometric bands of the Euclid with the BIS broadband, which basically covers the full visible, and 3 near infrared bands, plus for spectroscopy 2 grisms, which are called so-called blue grism and red grism, even though both are in the near infrared. I would like you to remember that Euclid has these 2 grisms because I will use them later. And finally, let me introduce you what I mean with empirical mocks. Probably when you think about simulations, you are more familiar with hydrodynamical simulations. Hydrodynamical simulations are defined because they start from well-known laws of physics and from well-known initial conditions and evolve these conditions with the known physics to create a universe which follows the laws of physics. This has a huge predictive power and allows us to test our predictive models. But, because everything has a but, the counterpart is that they are very computationally expensive. And also, they are highly dependent on certain implementations of baryonic physics, which are not exactly well known. For example, the physics of the central core of the AGN, and they rely on prescriptions to supplement this lack of knowledge. Here I'm showing some examples of hydrodynamical simulations, either dark matter only or full hydrodynamical with variance. So on the other hand, we have the empirical models. Empirical models are totally calibrated or at least mainly calibrated with observations. What is the advantage of this? Well, they are much computationally cheap than semi-analytical models or hydrodynamical simulations. They reproduce the observed physical properties because we made them with this purpose. And they are very flexible parameterization. The fact that they are computationally cheap allow us to change certain parameters and see how the result changes. How can we use these mocks? Well, they can be very useful for the next generation service that I presented before. We can use them to provide forecasts. This forecast at the same time can be used to optimize the observational strategies of the observatories, because when one designs, especially for example, a space telescope, you cannot go there and change things. It has a limit lifetime. You want to be sure that in the 10 years of the telescope, you will do the most out of it. They can be used to test and optimize the data analysis pipelines, and also to estimate incompleteness and biases in the data. We will see examples of this later with the catalog. So finally, arriving to the work I'm going to present here, I'm going to present an empirical catalog we call MAMBO. MAMBO, it's a workflow designed to build catalogs that reproduce with accuracy the observed properties of galaxies and AGN. And as I said before, it was built based on empirical relations. In the catalog, we include several observables and physical properties, such as broadband magnitudes observed at rest frame, SEDs from the near infrared to the UV, and several physical properties, stellar mass, dust, size, terraformation rate, etc. The LightCom, several LightCons, and also the code is public in GitHub, so you can go there and download it and play with it. So now I'm gonna explain you how we build this catalog. And the first step to build the catalog is to build the galaxy catalog, in which we will put the AGN later. To build the galaxy catalog, we start from a dark matter simulation, namely the Millennium simulation. We take the mass of the dark matter halos, their redshift and their position of the sky, and using a stellar to halo mass relation built with abundance matching, we populate these dark matter halos with galaxies. If you have questions about these words, I can explain you later, but I don't want to stop a lot with them. Then each galaxy is separated into star-forming or quiescent, and this is done based on observed stellar mass functions of quiescent and star-forming galaxies. And finally, the rest of physical properties, SD, observed magnitude, etc., are applied using the public code EG, Empirical Galaxy Generation, which we modified for several things, for example, to include AGN. So now we are going to focus on how we include AGN to this mock catalog. The first step is to define which fraction of galaxies are hosting an AGN. For this, we used observed duty cycles, that is, the fraction of galaxies with supermassive gas holes accreting above a certain ratio, for which we can define, okay, this galaxy is an AGN. Based on these observed duty cycles, we model the probability that a certain galaxy with a given stellar mass and with a given redshift will be hosting an AGN. So this axis is the probability. For example, at
Let me try one.
okay. Don't worry. I think it's once in a while.
When people say that in the streaming, part of the slide is cut off.
Ah, wow.
You can see this.
That's because I changed this. He's
I'm sharing
sharing
the
the
screen.
screen in Zoom. The problem
Now,
is
now it's looking good.
he has to stop sharing and share again.
Ah, okay.
Okay, now
Should I do that?
yeah, now you can do that.
Okay.
I can check.
Sure.
Now it works.
Now it works. Okay. Sorry, I stopped sharing in vain.
Yeah, now there's nothing.
Okay.
problem is that the polygon stopped working because requires an update and will not connect to Zoom.
Is it okay now on Zoom?
This is
Is it okay now?
Now I can only see a white stripe.
White, okay. Wait, let me see what I'm sharing. Okay, now I hope it's okay.
Now it's great. Now it's great. Yeah.
Okay, thanks. Okay, so now we have which fraction of galaxies are hosting an AGN. The next step is to assign to this AGN an intrinsic X-ray luminosity. This we do starting from observed specific accretion rate distributions. And I'm not going to bore you with the details, but basically with this, we can have an intrinsic X-ray luminosity assigned to each AGN. The next step is to separate this AGN into type 1 or type 2, specifically in the optical range, because we are making catalogs to be used mainly for optical near-infrared telescopes. So for this, we use this prescription from Merloni 14, in which they give the fraction of obscure galaxies in the optical as a correlated with the intrinsic X-ray luminosity of the AGN. Using this prescription, which is mainly independent of redshift, we separate all our AGN into type 1 in blue or type 2 in orange, here I'm giving the X-ray distribution for different redshift pins. Now the next step is for type 2 AGN, well, for both AGNs, we want to assign a realistic emission. How we do this? For type 2 AGN, we assign narrow AGN lines on top of the galaxy spectrum. We don't assign any AGN continuum for the moment. This is work in progress, but we have the lines. These lines come from cloudy photoionization models, in which we choose different parameters. For example, the metallicity, log U, NH, UV. We have it fixed. The UV spectral slope. Now to these lines, we assign a full width half maximum, which we assign as a log normal distribution, which you can see here, which more or less goes from 200 to 1000 kilometers per second from Menzel 16. And we give the emission line intensity, which is proportional ultimately to the intrinsic X-ray luminosity of the host. We assign this full list of lines. And with this, I'm showing you here one example in which you can see the host galaxy contribution in orange and in purple, the AGN contribution. Here I'm zooming in into the H beta and O3 lines. I'm here to show you some other examples. And we quantify the relative contribution of the AGN to the galaxy by the ratio of the lines. For example, for O3, 5008, here I'm showing an example in which the O3 is almost not dominating from the AGN side to the one in which the AGN practically dominates the full line emission. Now, for the type 1, it's a bit more complex because type 1, we know that it's not only their lines that dominate in the spectra, but also the continuum is very different from those of star-forming galaxies. So we constructed a library of type 1 AGN spectral templates from Temple 2021 with different emission line properties. Now, the code selects one of these templates, and we scale it to give it the proper UV luminosity that it should have according to the LX LUV relation. Again, this is an observed relation. And finally, we reddened the template following again an observed EV minus V distribution. The result is this. Here I'm showing one example in which you can see again the AGN contribution in purple, the host contribution in yellow, orange, and in cyan, the total contribution. Here I'm showing some other examples. In the case of type 1, we can quantify the contribution of the AGN with respect to the galaxy based on their broadband fluxes. I am showing here 3 representative examples from the catalog, let's say. This would be a classical quasar, a type 1 AGN, in which dominates in the UV and with prominent broad lines. Here is a type 1 quasar in which we can see the broad lines, but also it's some part of the continuum is dominated by the galaxy. And here we see what would be called a red quasar. It's a quasar with a big obscuration, which is not the common. It's not the common case because it's only a few of them. But it's a quasar which is very redent in its emission, but still it dominates over the host galaxy. So the next thing I want to show you is how we validate this catalog. That is, how this catalog compares with other observations that were not used to model it. First, we look at the X-ray luminosity functions because we start from X-ray selected samples of AGN in order to construct the fraction of AGNs. Here in purple, you can see the AGN from MAMBO with its error compared to several observations from the literature, from redshift close to 0 to redshift 7. And you can see that in most redshift bins, it agrees quite well with observations. Here I'm showing you the cumulative X-ray flux number counts. Again, purple is MAMBO, and compared with different results from literature, it compares quite well until quite low fluxes. Now to the UV and luminosity functions, because this is less of an input, we could say the X-ray luminosity functions are a bit more input, while this is not said that it should be preserved. And in fact, we have a bit more troubles to reproduce observed luminosity functions. For example, here we have some bumps that we are investigating why we have this. But you can see that until redshift 6, the luminosity functions follow quite well the ones from literature. Here, in case you are wondering why these two and these two are so different, well, this one, if I remember properly, they subtracted properly the galaxy contribution. So in this case, I'm showing only the AGN contribution, so we have to compare with this one. Also, we can look at the colors of the AGN we generated. Here I'm showing a color selection diagram, which is optimized for Euclid plus LSST colors from Visicello 2024. The selection is the gray line, so objects falling in this part of the selection would be selected as type 1 AGN. So in orange, I'm showing type 1 AGN, which are dominated by the AGN contribution. In blue, I'm showing the type 1 AGN, which are dominated by the galaxy contribution. And you can see that the ones dominated by the AGN contribution are more properly selected by the selection. As a comparison, the red contours show the data from Chandra Cosmos, selected with spec type 1. Another validation we can do is diagnostic diagrams. I showed you before that with the narrow lines of AGN, we can differentiate those AGN, the type 2 AGN from star-forming galaxies in this side of the diagram. So in red, you can see the objects which are dominated by the AGN contribution in their lines. And you can see that all of those objects are selected as AGN in the BPT diagram. And also in the next diagram, which has the same y-axis as the BPT diagram, but in the x-axis, it has the stellar mass of the host. We can see that AGN are also mostly properly selected by this diagram. Another validation that we can look at is there. Oops. Now it's
we switch back to the flickering.
For the people online, we're having.
I'm going to check if the frame is You have to stop sharing and share again.
Okay.
This is terrible.
No worries. It's the classic astrophysics. We can send telescope to space, but we cannot.
Set up a device.
Yes.
El adaptador está un poco chamuscado, por eso haces el linking.
Sí, pero el linking no lo hace cuando está conectado
Está
a
bien.
Pólico.
Ya. Algo,
O sea que
hay algo de
Tiene
ruido
algún
ahí.
problema cuando está conectado a un ordenador.
Mm.
Que debe tener otro tipo de corriente o contacto.
Sí,
o algo así.
yo creo que
Is it okay now?
Yeah, it's okay.
So another validation, and this is the last one I'm going to show, we can look at is the clustering signal of this AGN. Here we are looking at the projected two-point correlation function of AGN, which for those of you like me don't know a lot about cosmology, this measures the probability excess of finding an AGN pair at a given projected separation compared to a random distribution in which there is no clustering signal at all. So the shaded lines show data from literature with each error, while the points show being the
Do you prefer this or the black and white? But it's connected exactly as before, so I don't know why he's responding differently.
I was using it and it was blinking in my computer, but not so much. I mean, I've been working with it 3 days.
No, it's a problem of the cable, but. Okay. Try this. Vamos a probar aquí. Okay.
Y si presentas, igual de ese programador es más fácil y
Podría compartir yo la pantalla, sí.
bueno, sí.
Mira,
Ah, perfecto. Ah, perfecto. Sí.
Tienes que dejar de compartir, compartir otra
Sí,
vez.
vale, espera, vamos a
Ah,
cambiar.
vale.
Déjalo ahí que ahora mismo.
Vale.
Ahora está bien, ¿no? Ahora si quieres.
Vale, debería estar bien, ¿no?
Sí. Ok.
Vale, sigo. Okay, so basically to be fast, the AGN from MAMBO follow quite well the clustering signal from literature. Even though this was also not an input at all, this just we didn't input any clustering signal into our catalog. It's just because the galaxies are on top of the dark matter halos, and because of the way we input the AGN, this is kind of a consequence of that. Oh, no. Okay. No, wait. Okay, sorry. Okay. So now we can move finally to a bit the more exciting part, which is, okay, all of this work, how can we use it? So at the beginning of the talk, I told you one of the uses of this type of catalogs is to provide forecasts. So, okay, this is a bit of a messy figure, but I will try to explain. Here I'm showing the H-band magnitude number counts of different types of populations. In green, we are showing for MAMBO galaxies. In blue, solid for all MAMBO AGN with any selection. Okay. And now the lines show different selections. For example, the orange, the orange line show MAMBO AGN type 2. I didn't write it here. I should have written it somewhere. But with selected with a X above a given X-ray flux. Why we did this? Well, to compare with the ones from Cosmos, which are also selected about a given X-ray flux. If I remember properly, both of them is 3 × 10⁻15 X blah blah. And we use this also as an extra comparison about with the orange and red line. Same for type 1, in which you can see the MAMBO ones in green and the cosmos ones in yellow. Okay. And with this, we can provide forecast of, for example, for the Euclid telescope, which will have the wide survey that I said before. The wide survey will be limited at H magnitude 24. So we can get the counts. Okay, for in the wide survey with H magnitude less than 24, which is this is the total area of the survey. Which density of AGN do we expect to find? Which total number of AGN do we expect to find? Same for the deep surveys. Another type of forecast we can do is how will the diagnostic diagrams look when observed with Euclid. For example, here I'm showing the BPT. For example, you focus on this panel, you see the BPT for the deep survey, and we can see how many AGN will fall in this side. Disclaimer: this is if we use the intrinsic fluxes of the AGN. This is without applying any noise from the Euclid spectra, any spectra extraction, etc. Which is what we are gonna see next, because another thing that I said at the beginning that we can do is to test and optimize the data analysis pipelines. Again, we are focused on Euclid. So here, for this exercise that I'm going to show, we generated some Euclid-like spectra. When I say Euclid-like spectra, what I mean mock spectra, that's simulated spectra, that mimics the spectra that is already being captured by the Euclid NISP instrument and incorporating as many instrumental and environmental effects as possible. What is our goal with this exercise? We want to test the official Euclid pipelines and test their performance at recovering key spectral properties, such as line fluxes for width hash maximums. How we generated this Euclid-like spectra? We used a bypass code called FastSpec, which basically what it does is, if you want to generate Euclid-like spectra, you would start from a mock catalog, simulate a 2D spectra, then another Euclid pipeline will extract the 1D spectra from it. Then another Euclid pipeline analyzes this spectra and give you the flags for width of maximum, equivalent width, etc. Instead, with FastSpec and with our mock spectra through FastSpec, we apply the instrumental environmental effects to produce the 1D spectra. And then we ask OUSP to analyze this spectra. Here, I'm showing you some examples of this simulated AGN. In black, you can see the incident spectra, that is the one from MAMBO without any noise from Euclid. Here you can see for type 1 and for type 2. Why the red and blue lines? Well, I told you before, remember Euclid has these two grisms, the blue grism and the red grism. So this is what the different colors represent. You can see as objects became more faint, signal to noise ratio decreases, and the noise starts to dominate, and we cannot detect any lines. For example, in this one, in which there was a broad line in the original spectra, most probably this is not recovered. Here I'm showing the same for type 2 AGN. Okay. Which type of analysis we can do with this? Well, because we know the intrinsic flux, because it's an input for us. This I'm showing only for type 2 again, by the way. We know the intrinsic flux of the line. We know the one that it's measured by the Euclid pipeline, and we can compare those. We see that, for example, for H alpha and H beta line, the measured flux, even measured when we measured on the incident spectra, tends to be underestimated. Why is this? Most probably is because the pipeline does not include corrections for absorption for the hydrogen lines. Okay. While we see that, for example,
Do you want me to try with this?
I think, well, whatever you think, I think we
How
can,
much time do you still have a talk? How many more slides do you have?
not so many, we are towards the end.
Okay, let's
Go ahead.
Well, maybe like 20 slides more, but towards the end. While for the nitrogen and oxygen lines, this does not happen. That's why we guess it's from the absorption, but again, this is still under investigation. When measured on the fast spect output, that is the Euclidized spectra, because this column measures it for the incident spectra. When measure the fluxes on the Euclidized spectra, we can see, of course, that the result is much more noisy. Okay, so with this, we can see how the BPT diagrams would probably look with a realistic Euclid spectra. Here I'm showing for the wide and the deep surveys we have, which have different depths. Okay, I think we can try to change the. Yes.
It's getting worse.
So we should use this? Or?
Yes.
Although. No? Ah, okay. Because you see, the problem is this one.
But the problem is the cable, so we don't know how it's going to respond with a different.
And this I'm not sure if.
It's still flickering.
¿Cómo? Para. Opa. Teclado no puede ser. I think this. Creo que se piensa que esto es un teclado y lo tengo. Voy a darle a omitir y ya está. A ver. Esperemos que funcione. Vale. From home. Should we.
You have to talk,
Okay.
but wait a second because it's not really working.
Yeah.
That is.
So let me try again. So the polygon was working and now it's rebooted. So let's try again with this.
Okay.
Not usually like this.
Okay.
No, it was stable for some time. But it's okay.
Okay.
Online is okay.
Yes. That black line is not mine.
That's the adapter idea.
Also, I just changed slide. It's not.
Yeah, it changed it.
Change the home, right? Like, evidently. What if
If not, I
Yeah.
will. I will
maybe
share with this.
yeah, maybe you can project your screen there and I just share on Zoom.
Cambia la entrada, Juan, por última vez y ya está. Es que es ese que falla. Es
Sí,
verdad
pero-
que.
Tú puedes compartir tu pantalla de ahí a
Lo que
ahí.
voy a hacer,
Que a ver ahora.
Pues si tú puedes proyectar tu pantalla y tú tienes la de Zoom al final.
for the week tomorrow, is it okay? Unless it's updated somehow, it's not going to.
Bring that transparency.
Press with transparency. So
Yes, I'm the only one. So we need to go back to the distance.
Let me start with I things.
Okay, perfect,
Okay. Go ahead,
perfect.
if you can.
Keep that.
Let's do. Okay. So, okay, let me come back quickly to the slide. So we were saying we have the flux measured by this official Euclid pipeline, both measured on the incident spectra, on the black, and also on the output spectra, right, on the Euclidized one. So now we can do the BPT diagram, and why I have 3 rows. Okay, let's focus, for example, on the white survey. The first row shows you with the flags from the catalog, that is the one, the true value, the ones that we use as input. Then on the second row, we are showing the BPT diagram constructed with the flags measured by the official Euclid pipelines on the intrinsic, on the incident. This already will tell us about the bias produced by the pipeline. While on the third row, we see the BPT diagram constructed with the fluxes from the Euclidized spectra. These tell us both about the bias from the pipeline and from the instrumental effects. I'm gonna keep this to be fast. Okay, I'm gonna go to the final exercise that I'm gonna show you of example that we can do with this catalog. I'm gonna show you an example of photometric redshift. In case you are not familiar with photometric redshift, a very quick introduction. Usually, when we want reliable redshift, we want spectroscopic redshift, but many times getting a spectroscopic redshift for billions of galaxies is just not possible. So photometric redshift instead is a great tool. How are they estimated? They use broadband photometry to use to explore the broad features of one of the spectra to measure the redshift with it. To give you an example, and if this works, will be a miracle, but I hope it does, because this will animate. Here, if you see the different colors of different filters, and you will see how as the redshift of this template spectra changes, the magnitudes will change. Okay. So specifically for this work, what we did, our goal was to retrieve photometric redshift from perturbed Euclid and LSST photometry. For this, we use phosphorus, which is the official Euclid tool to do this. It's a template fitting algorithm to estimate both photometric redshift and physical properties from Euclid and ground-based photometry. And to estimate the performance, we used standard metrics, the normalized median, the fraction of outliers, and the median. The fraction of outliers, which I will mainly focus on it later, tells you how many objects are catastrophic failures of the measure of the redshift. So before we go into the results, I'm going to show you how the perturbed magnitudes look like. Here we are showing the intrinsic magnitude from MAMBO against the perturbed magnitude. And you can see how above below signal to noise ratio 5, it's much more a messy situation. Above signal to noise ratio 10 is much better. All the results I'm going to show you, a disclaimer, are for signal to noise ratio greater than 5. Okay, if I show you results for signal to noise ratio greater than 10, the results would be better. I'm showing you kind of the worst case scenario. So first, how well does it work for galaxies, which would be like our standard sample, let's say. If we use as templates for the template fitting pure galaxy SEDs, we see a fraction of outliers of 25% around, which decreases to 13% if we use a signal to noise ratio greater than 10. For type 2 AGN, the fraction of outlier is less. Why is that? Most probably because the narrow lines emissions that we added do not add a lot to the broadband photometry. Instead, AGN are a subsample of the bright galaxies. So that's most probably why it's working better for type 2 AGN. Now, if we go to type 2 AGN, in which we say the continuum is very different from those of galaxies, we separated our sample in two. Those dominated by galaxy component, those dominated by AGN component in the H band. We can see how for the ones dominated with the AGN component, as we could expect when using galaxy templates, we have a catastrophic failure for most of the objects. Okay, so what we did, we tried, what if we change the templates? It's a first obvious attempt. Instead of templates only galaxies, we can use a template with mixed galaxies, AGN, and also hybrids. So for the same sample, the ones dominated by AGN, we see that the fraction of outliers decreases to 34%. But we can still do better than this if we apply a prior. In this case, for example, with a luminosity prior that tells you all of your objects, because they are type 1 AGN, they should have a B magnitude, which is in this range. The code uses this prior, and then it gives you a better fraction of outliers, which is actually comparable to the one we have for galaxies. So what are the conclusions from this experiment? Well, we see that it is fundamental to select the appropriate templates and priors if you want to have the correct results in the photometric redshift. Also, it can help a lot if you can classify your objects into galaxies or AGN before trying to retrieve the photometric redshift. And this could seem obvious, but why is this exercise helpful? Well, in practice, it is not always possible to observe to define how much a source is dominated by galaxy or by AGN component. Here we have the information because it's a simulation, but as you all know, in observations we don't have this information. So this exercise gives us a hint of how biased we are when we are not using the appropriate templates and priors, which as we saw, it can be really biased up to almost 100%. So this is basically all I wanted to show you. To summarize, we built an empirical catalog of AGN and galaxies using empirical relations. The catalog includes several observables and properties, such as magnitudes, SED, physical properties, etc. And we showed how this catalog can be used to provide forecasts, to test data analysis pipelines, to estimate potential biases. You can read much more of this on the paper that was published last year. You can download the icons or the catalogs in GitHub, which disclaimer, it's under construction and will be improved, but you can still already download the catalogs. So this is all I wanted to show you. Thank you very much for your attention.
Thank you very much, Xavi. Millions of apologies for the million interruptions.
Don't worry.
Questions? Lena?
Thank you, Xavier. Very nice work. It's amazing that we put all of this in only one paper.
Actually, the paper doesn't have a lot of this part, actually.
Okay.
Most of it will be in my thesis, but part of it is not in the thesis. Most of the applications that I show with the photometric redshift and with the Euclid-like spectra is not in the paper.
I was curious to see when you showed the AGN spectra, the incident ones and the recover.
Yes.
Can you look at that slide?
Like-
Yeah.
The-
I was curious to see on the upper left panel the drop in the flux.
Yes. Yes. This is because FastSpec assumes a fixed extraction window for the extracting from the 2D spectra to the 1D spectra. And for very bright objects, you are missing so this exactly. So this is bright, this is faint objects. So for the bright objects, you are missing a big part of the light.
I guess that will have implications for the.
So in principle, what I have been told is that Euclid right now uses, I mean, this was used for the simulations, For the real data, you should use optimal extraction, which changes the extraction window proportional to the brightness of the.
Related with this, actually, I would have several questions. I'll try to
Yes.
only focus on two. The first question is, what is the resolution of the spectra?
380
Okay.
R.
And if this follows up on Elena's question, just to extract the AGN, if you can also see the galaxy,
Yes.
you have to adapt the aperture not to the magnitude but to the PSF.
Yes. So the way, okay, I'm not 100% sure about this because fast spec is really complicated, and I just worked a bit with it. I think the way fast spec works is you give it as input only one. You give it as input only one spectra, which represents the.
It's a one-dimensional.
Yes, it represents exactly. It represents the spectra of your source. You cannot give different spectra for the source, for the nucleus, and for the host galaxy, and say the size of each component. So
And now skipping to the photo-Z part.
yes,
Let me see if I understood what you showed right. So you're using at the same time all the photometry.
yes, yes, yes,
Okay, so from U to Euclid H.
yes, exactly.
Okay. So you're assuming that one object is observed both by
Euclid and LSST.
Euclid and
Yes, yes, yes. This would be if we have both Euclid and
Okay.
ground photometry.
And the signal to noise 5 is in all the filters? All the filters can
Yes.
be 5 or
Yes, yes. With all filters, yes, yes. Selected our signal to noise ratio 5.
More questions? I have one. So the idea is that when the surveys are done and the data comes, you will come back to this and fix the things that were not predicted correctly, so you can use the same environment for a future mission after Euclid.
Yes, that would be.
Let's say, for example, after Euclid, you can improve this and prepare for Roma.
Yes. So I don't know if how much I'm personally gonna keep working on this catalog. I don't know, depending on contracts, etc. But yes, ideally, yes, that would be the plan to keep developing this based on new data.
In the BPT diagram
Yes.
that you show the three different measurements. Yeah, here. So this means that very few AGNs will be clearly detected with the spectroscopy of Euclid, right?
Yes, which again, all of this should be taken with caution because this is well, sorry.
One question.
Yes.
How many AGNs do you simulate? I think we need the number.
So okay, so for this, yeah, I didn't give a number for this. We start with a small sample. For actually, the sample which I gave to FastSpec was 1,000 type 2 AGN, and this translates into when we do the proper selections for the white PPT, white service, etc. We get these numbers. The real sample was 1,000. In the full catalog. Okay, I didn't say this information. The catalog from the Millennium Lycon is 3 square degrees, and there, if I'm not mistaken, we have of the order of 10,000 AGN. not all of them with spectra, but it can be generated also. Because when one runs egg, the code, you can decide if saving the spectra or not. We don't have spectra for all of them because it's the heaviest part, of course. But eventually, you can select for which agent you want the spectra and run it and download it easily. We did some other experiments also by applying the same methodology, starting from instead of from the Millennium light cone, which is only 3 square degrees. You probably know the flagship for you, which is the hydrodynamical simulation built for Euclid. So we started from 30 square degrees to have a bigger sample of from the flagship. And in that case, we had many more AGN. I don't remember, but on the order of 100,000.
And why did you decide to stick to any?
Well, we want to start from a dark matter simulation. From flagship, what we did is we take the galaxy already, the galaxy catalog from flagship and populate it with AGN. Well, we wanted to have a workflow that can work from the dark matter simulation to the end. We would like to try with bigger light cones. Yes. The one we tried with the Millennium, which is 3 square degrees.
Questions? No? Let's thank you again, Xavi.
Thank you.
Especially for the patient.
Yeah.